Welcome to Lecture 3 of Introduction to Robotics, subject ENB 339 at QUT. Today's lecture is on forward and also inverse kinematics. So in the past lectures, we've already looked a little bit at forward kinematics. So forward kinematics is about finding the position and orientation of the tool point, generally that bit at the end of the robot arm which does the useful stuff like picking up stuff or welding and so forth, finding out its position from the joint angles along your multi-armed robot. So that's what forward kinematics is about, going forward from the base of the robot towards the tool point at the end of the robot's arm. The inverse kinematics are essentially the complete opposite of the forward kinematics, and these are much more relevant to most of the real-world applications and tasks that you'll find robots doing. And simply put, inverse kinematics are about finding what particular angles you should set for all your robot joints in order for the tool point at the end of your robot arm to be in a certain position and a certain orientation. So this is the sort of math that you're interested in if you know that your tool point has to be at a certain location and a certain orientation to do a useful task, such as painting something, for instance, and you do this math to work out what angles you should set your joints at in order to achieve that task. One of the big differences between forward and inverse kinematics is that forward kinematics usually has one distinct solution. So if you set all the angles of your joints for a robot arm to certain values, then usually there's only one particular position that your tool point will be in. Inverse kinematics, however, is quite different. There are often, depending on the situation and the design of your robot arm, many different ways that you can position your robot arm joints and angle them in order to reach a certain point in the workspace. And a good example of this is if you think about your arm, which is a form of robot arm, and think about all the different ways you can position your shoulder, your wrist and your elbow joint in order to reach a certain point in space. Now, to make all the math as easy as possible, and that's what we're really interested in, there's a convention that is used widely for how you label the joints and links in a robot in order to set it up for you to perform some math to do some useful things. So link 0, there's always a link 0, and this is called your base frame. This is usually where the base of your robot is often attached to the ground or a tabletop. And its reference frame 0, it has x0, y0, z0 as its coordinates. Joint 1 is positioned where reference frame or link 0 is, and joint 1 has a joint variable. In this case, because it's a revolute joint, it has a joint variable called θ1. Joint 1 actuates or drives link 1, which has that joint variable θ1, and link 1 has its own reference frame, in this case positioned at the end of link 1, called x1, y1, z1. And then joint 2 is positioned at the end of link 1. So the joints in general join together links, and joint 2 has its own joint variable, θ2. Once again, it's a revolute joint here, and so forth. So this is the general convention for labeling joints and links, and it pays to get the numbering right. Also note that later in this presentation we'll talk a little bit about a specific way of making sure you orientate the axes correctly in order to make your math as easy as possible. So each joint, as you saw in the previous diagram, has a joint variable, and we use Q subscript I to denote the ith variable for joint, well, the variable for joint number I. Joints can either be revolute or prismatic. In that last diagram I showed you, all the joints were revolute, but they can also be prismatic. And what you can form, and this is building on what we did in our last lecture is you can form a general transformation matrix, which shows the transformation from reference frame I-1 to reference frame I. And this is written as A subscript I. It's a function of the joint variable Q subscript I and other things, and it's derived from both joint and link number I. Now, of course, you usually have many joints and many links in a robot, and you can chain together all these transformation matrices, A1, A2, all the way up to AN, depending on how many links and joints you have, to form a kinematic chain and form the overall transformation matrix, which we generally use the letter T to describe the transformation from reference frame N to the base reference frame 0. And it has the same general matrix form. In the top left, you have all the parts of the matrix responsible for doing rotation, represented by the R. And at the top right, you have all the displacement transformations in terms of how the various origins of the reference frames are displaced relative to each other. So, in order to calculate the forward kinematics, so work out these transformations, you could just draw detailed 2D or 3D diagrams of your joints and links, and just use geometry and your knowledge of geometry and trigonometry to work out what the forward kinematics are. Of course, as your robot arms get complicated or they're arranged in complex configurations, this gets very hard or impossible for most people. So what we need, and this is a general theme running through this whole subject, is we need an approach which everyone can apply in the same way or in a very similar way with standard rules, which makes the math as simple as possible so we're least likely to make mistakes. So the convention we use to make life a bit easier for us and everyone else is called the Denavit-Hartenberg Convention. So first of all, a general transformation matrix has 6 variables, 3 in the rotation component, which is at the top left, and 3 in the position or displacement vector. This Denavit-Hartenberg approach, or DH is what most people call it, collapses these 6 variables to only 4 link parameters. But this only works if we follow a certain process or procedure for how we set up these X, Y, Z coordinate frames at each link. And the 4 parameters for each link are A subscript I, which is the link length, alpha subscript I, which is the link twist, D subscript I is the link offset, and theta subscript I is the joint angle of joint I. So the first 2 parameters are generally fixed for a particular link. Even if the robot is moving around, these parameters are pretty much fixed. They would only change if you took apart your robot and maybe made the arm half as long or twisted it and changed it in some permanent way like this. The last 2 parameters can change. So for a prismatic link, which extends or contracts, D would change, and for a revolute joint, which rotates, the theta parameter would change. So what we can do is, for these 4 parameters, the theta, the D, the A, and the alpha, we can look up the appropriate transformation matrices, which we've already looked at in our last lecture, and multiply them together to get an overall transformation matrix for that link A subscript I. And that's what's actually been done in this slide, and you can go and check the matrices as some work after the lecture. So I said before, there is a cost, of course, to using this simpler system where we've only got 4 parameters instead of the usual 6. And this is that we have to follow a certain set of rules when we assign reference frames to each of our links. So rule number 1 is that the Z I-1 axis is the axis of actuation of joint number I. So if it's a revolute joint, then the axis Z becomes the axis of revolution of that joint. If it's a prismatic joint, then the axis of translation is represented by the ZI-1 axis. The second rule is that once you've set these Z-axes, you set your XI axis so that it's both perpendicular to and intersects the ZI-1 axis. Note that it's the XI axis relationship to the ZI-1 axis. And then rule 3, which is just a cleanup rule, is that using your right hand rule, you can derive what Y subscript I, what the Y axis is, from the already defined X and Z axes. So for your base frame, which is the base of the robot generally, you assign the Z0 axis to be the axis of actuation of joint 1. So in this diagram, Z0 has been assigned to a revolute joint to represent the rotation of that joint. X0 and Y0 can really be set anywhere you want them, as long as they satisfy the right hand rule, but usually to make your life easy, you align them with parameters or parts of the environment. So for instance, if your robot's sitting on top of a table, you might align the X and Y axes with the two sides of the table, for example. If you're assigning these axes to the tool frame, so for instance in this picture we have a gripper, what you can generally do when it's possible to do so is to apply the Z-axis to the approach direction of the tool. So this is the direction that the tool would come in from as it went to grip something. Y-axis is the slide direction of the gripper. So this is the axis along which the two prongs on the gripper move outwards or inwards to grasp something. And X is assigned as an afterthought as long as it satisfies the right hand rule. For rule 2, case 1 is that ZI-1 and ZI are not coplanar. So in this diagram showing two reference frames, ZI-1 and ZI don't share any common plane. And in this situation, there's only one possible XI axis. And this is the line which is the shortest line from ZI-1 to ZI. And the origin of reference frame I is at the intersection of Xi and Zi. The second case when you're applying rule 2 is that you might have two Z axes which are parallel, like in this diagram. So in this diagram they're both pointing in the exact same direction. In this case you could set Xi to any one of a number of possibilities, but you want to make your job as easy as possible, so usually but your best option is to choose an Xi axis that passes through the previous reference frame origin. We do this because it means that one of our parameters, d subscript I, becomes 0. And zeros are good, they make our math easy. O subscript I, the origin of reference frame I, is at the intersection of Xi and Zi, and alpha I, the twist parameter, is always 0 in this case. So that's good. That's another 0 parameter to make the math much easier when we have to go multiply matrices later on. Case number 3 for applying rule 2 is when your previous Z-axis intersects with your ZI axis, as shown in this diagram. So what you do in this situation is you set your Xi axis to be normal to the plane that is